how do we know when to stop iterating? After each iteration, we calculate a residual R, and if that residual is less than some tolerance that we pick, we stop iterating. And we will use a tolerance of 10 to the power of -6. So to calculate this residual, we first calculate an unscaled residual and then scale it to get the residual that we use. So first let's take a look at the unscaled residual. That's defined in this way. So we go to the jth cell, we take the current value, and then we take the value at the end of the previous iteration and we find the difference. So this is how much the value in the jth cell has changed in one iteration. And we take the absolute value of that. And we add this over all the cells and we divide it by the number of cells. So this gives us the average change in value per cell during one iteration. It makes more sense to use a relative change rather than the absolute change. And so we take this and we scale it by the average value of the absolute magnitude of U for all the cells. So we pull out the absolute value of Uj from all the cells, and then we take the average of that. And we use that to scale our residual. So the unscaled residual by this average value gives us the residual, the scaled residual that we use to check if our iterations have converged. And so substituting, this into here, we get this final expression. And that is a relative change in value per cell during one iteration. And if that is below the tolerance, our update is small enough that our guess is sufficiently close to the true solution. Let's see how all these ideas come together in an algorithm. And the particular iterative methodology that we have been discussing is called the Gauss-Seidel iterative technique. Here's the algorithm. You keep track of the current iteration number using this counter. So you initialize that counter. You also initialize the cell center values for all the cells. So this is the initial guess. Then you begin the iterations. You increment the iteration counter. You save a snapshot of the current cell center values, and you do that to calculate the residual. Then you go to each cell and you update the cell center value using the current guesses, and you assign it to the U array. Okay, so the initial guess in the U array gets overwritten by the current update. And then you calculate the residual by comparing the current cell center value to the value at the previous iteration. If the residual is less than a tolerance, you have driven the guess sufficiently to the true solution or on that mesh. And so you're done. You can stop iterating. Otherwise, you come and check if your iterations have exceeded a maximum number of iterations that you specify. And you do this to prevent from iterating forever, going into infinite loops. And if your iterations have exceeded the maximum number of iterations, you stop before convergence. Otherwise, you come back here, and you repeat the iteration process. You increment the iteration counter, you save a snapshot of the current cell center values, and you update the cell center values using the update equation, and keep iterating. Here's a Matlab code that implements the Gauss-Seidel iterative technique for the nonlinear channel flow equation that we've been considering. And first let me run this code. And let me move the legend out of the way here. So the solid line is the linear case, and then the symbols are the nonlinear solution on 3 different cell counts. So you can see that as I refine the mesh, my solution changes a little bit, but it's not changing a lot. So by the time I'm at 12 cells, I seem to be, getting close to a good level of mesh refinement, but I might want to do 1 or 2 more levels of refinement. And also, as opposed to the linear case, I see the effect of the nonlinear term, which is to add a drag to the flow. So that is as expected. And if I go and look at the residual variation, so this is plotting residual versus iterations, and the residual is plotted on a logarithmic scale. So which means that a straight line in this plot means that the residuals are falling exponentially. And that is a desirable trait, but you rarely see this kind of exponential decrease in the residual in a real CFD calculation. The other important thing to notice here is that as you refine the mesh, it takes a more number of iterations to converge. And that's typically what you would see in a real CFD calculation. Going back to my code, so here, I'm defining what are the cell counts at which I want to do my finite volume solution. This is the exact solution for the linear case without the nonlinear term. I've written a function called fvsolve to get the finite volume solution, and I call it with 3 different cell counts. And so this is all the plotting stuff once I get the solution, and this is the function that where I'm doing the finite volume solution. Here's the meat of the code. So first I initialize the cell center values for all the cells, and here I'm just initializing all the cell center values to 1. Then I start the iterations. I save a snapshot of the current cell center values in this array, and I do that too for the residual calculation. Here I'm updating the first cell at the boundary. Within this loop, I'm updating all the interior cells. So this loop goes from 2 to n-1. So this is implementing, these 2 lines are implementing the update equation for the interior cell, for the jth cell in the interior. And to evaluate the right hand side, we use whatever value is contained currently in the cell, and that's in the U array. And so we pull out the appropriate value from U array, evaluate the right hand side, and then assign it back to the jth value in the U array. So which means that the U array always contains the latest cell center values. And similarly, we do this for the nth cell, which is the cell at the top boundary. So after we are done sweeping through all the cells, we calculate the residual. And if that residual is less than the specified tolerance, we have convergence and we can stop iterating.